and then we will be into a review period and then the test. I do have textbook review questions that I'm going to assign. They'll come up at the end of the last note here today. And I also have a couple of review sheets that were really designed more for the grade 10 applied class, but you know what, they're kind of useful, and I'm going to put them on Google Classroom, and I'll post that very soon as well, so that you can look at those and start to think about reviewing for the test. Okay, so yesterday we talked about, or we didn't, well, yeah, we did. We talked about what acids and bases are. Acids, they begin with H, things like HCl, hydrochloric acid, and bases end in hydroxide, OH, things like sodium hydroxide or ammonium hydroxide. We then did a little activity where we looked at some of the properties, and most of us got it done. Actually, I think we all got it done quite effectively, and some of us even turned that in last night, and that's excellent. Again, those are easy marks in terms of that little activity we did yesterday, and that's due today, so be aware that you want to get that finished. So, bromethymol blue. What color is bromethymol blue in an acid? Anybody remember from yesterday? Bromethymol blue in an acid? Anybody remember? Really? Absolutely nobody? Somebody's got it. What was that? It turns what? Red? Nope. Bromethymol blue does not turn red in an acid. What's that? Yellow. It turns yellow. It's yellow. Yellow. Phenolphthalein in an acid. Anybody remember that one? Phenolphthalein in an acid. Phenolphthalein was colorless. All right, Ashley's nailing this, so somebody's better step up to the plate here. Somebody else. No? Yes, no? Litmus. Litmus. What color was the litmus in the acid? Ashley? 50-50. Two colors to litmus. She's right. What is going on here? Somebody's feeding her answers. Litmus becomes red. Which means if it was a base, what's the litmus? If it's the base, what's the litmus? It's blue. And that's how you can remember, right? Litmus is always red or blue. And in a base, it's blue. And they both start with B. Base, blue. Nice and easy. And so the acid is red. They react with metals to form. What happened when we put the magnesium in the acid? What did it do? Don't let Ashley answer the question. Come on, somebody else wants to answer that. Come on, Josie, look at Ashley's getting these all right. What happens when you put a piece of metal in an acid? It fizzes. Now, I didn't have you test the gas, but the gas is actually hydrogen gas. I know it because I have tested it before. So I'm telling you, I'm giving you my insight in this case. So I'm telling you that it does produce hydrogen. If we were to put a bunch of magnesium in a larger amount in a test tube and put our thumb on it and then bring that splint to it, it would pop, and that pop is the positive test for hydrogen gas. In actual fact, when we did our gas test, when we were doing chemical and physical reactions, that was the reaction we did. We put magnesium in an acid. I didn't tell you that, but that's what we did. All right. Reacts with carbonates to form, and that was the sodium bicarbonate. And the sodium bicarbonate, which is baking soda. And again, it fizzes, but it produces carbon dioxide. Again, we didn't test it, but I've tested it in the past. So when we react an acid with a carbonate, that actually produces what we call hydrogen carbonate, which is what makes pop fizzy, and that produces carbon dioxide. That's the same reaction that you would use if you were making a volcano. Anybody make a volcano for a science fair project? That's so cliche, isn't it? No? You know, if you've ever watched Disney teenage TV, I hate it. I hated it when my kids watched that stuff. What was it? The Sweet Life? No? With Zach and you focus. Thomas, you focus. You have to write your quiz. You don't get to participate in fun conversation right now. Sweet Life with Zach and Cody. Thank you, Thomas. No, there was a science fair thing on it. Of course, somebody makes a volcano. Do you know what I'm talking about? It fizzes all over the place. Everybody knows what I'm talking about. Okay. The classic reaction that you put with that is vinegar and baking soda. Have you ever heard of that? You put the vinegar with the baking soda, makes lots of bubbles. That is the exact reaction here. The vinegar is the acid, and the sodium bicarbonate is a carbonate, and it produces carbon dioxide. That's what makes all the bubbles, and it comes out the top if you're making a volcano. Put a little bit of red food coloring in it, and you've got lava. Okay? All right? We could do the same with a rock that contains carbonates, right? So if you drop a rock in some pop or in some acid, it'll fizz, it'll bubble. Chalk is calcium carbonate, right? It's not sodium bicarbonate, which we use for baking soda, right? But this is calcium carbonate. It would do the same thing. Put it in an acid, it would bubble away, all right? And produce carbon dioxide. We didn't taste them, but acids do taste sour. You can think about some properties of, or some acids that we do ingest, things like vinegar, things like citrus fruits, like lemons. They all tend to be sour. They are electrical conductors, so they have the ions that can move around in the solution, all right? The term we use for a solution that can conduct electricity is an electrolyte. You've probably heard of that maybe in some commercials that involve things like Gatorade or some kind of powered sports drink. You know, they say you need to replenish your electrolytes. And again, you know, our bodies use these electrical conductive solutions so that our nerves can send electrical impulses, et cetera, et cetera. But acids, they will conduct electricity. And they can be corrosive. Again, corrosive means they can react with metals, and they can break that metal down. Okay, let's write down some properties of bases. Too far. Right there. Now, we already know litmus. I gave you my little way of thinking of it. Base, blue. Both start with a B. So whether you put blue litmus in a base, it stays blue. Put red litmus in a base, it turns blue. But you can use that same trick for bromethymol blue. What was the color when it was in a base? Blue. Now that's a coincidence. There's nothing special about indicators and bases and being blue. That's just a coincidence. That particular indicator, bromethymol blue, is blue in a base, and red litmus happens to be blue in a base. Coincidental. Nothing special about the color of blue and bases. Phenolphthalein. What was that color? What was the color? I went back and watched bits of the video when we were doing the lab because I was afraid I maybe had said something not so nice and I didn't want to put it out there on the internet, as your parents might be listening to it. And I stopped at the discussion on the color that we talked about. Yeah, magenta. I'm putting pink. You can put magenta, and I will give you magenta on a test. You can even put fuchsia. Pretty color, not specific enough. If you want to put a pretty pink color, sure, have at it. Look at, I have issues with spelling, all right? So let me use the word pink. I'm just putting pink. You can put whatever variation on pink that makes you feel good. Yes, sir.
Yeah, I have a question about question 6.
Yep, I'll be right there. You guys should finish writing that down.
I wanted something.
It's not very long. Right? I'm videotaping here, so don't be careful on what you say. We'll put the microphone way over here. Anyway, okay. All right. Taste bitter. Bases tend to taste bitter. Do we taste bases? Sometimes. Coffee is a base. It has a little bit of a bitter taste to it. If you've ever tasted baking soda, anybody ever tasted baking soda, like straight up? The people who, like to use all natural whatever, they sometimes say, brush your teeth with baking soda. It's a natural whitening agent. No? You ever heard such a thing? You can actually buy toothpaste with baking soda in it. You ever see that on there? It's bitter. It's not a very pleasant taste. So baking soda would be a base that you could taste if you'd like. Don't taste bleach, please. Don't do that. Not a good thing to do. It would be very bitter and bad for you. It would be resulting in a trip to the hospital. So don't do that. Feel slippery to the touch. Many cleaning agents do use bases. Bleach is one. But things like ammonium hydroxide is found in like window cleaner and things like Fantastic, if you ever use that type of a spray cleaner at home, or things like Pine Sol. So if you've ever actually, cleaned, say, the bathroom, which I laugh because I know my kids never clean the bathroom, so I know you guys never do. But, if you ever decide to help your parents clean up the house once in a while, and you end up getting some of that cleaner on your hand, when you go to wash it off and you wash your hand, you'll find that it's slippery and slimy, and that's because they tend to be made of bases, all right? They're also electrolytes, and they also can be corrosive, right? Bleach can be quite corrosive, especially when it's concentrated. Okay, so those are some properties. I just wanted to get them kind of written down officially. Yep. What? Okay. Let me move on to my second PowerPoint here, and let's do pH next. Let's do the pH scale. So I'm going to bring that up, and you guys can start writing that down. I'll talk about what's happening there. Okay. This is a good question. So I'll put the answer kind of up on our PowerPoint here. The question was, could you use like an acid or a base because it's an electrical conductor to charge your cell phone? Is that what you're asking? Okay. So essentially you're asking, can the acid or a base be a power supply? Right? So like if you were to plug something in. Okay. Here's the answer to that question. And this is more detailed than you guys need to know for this course, but it's a really good question. All batteries, even the batteries in your cell phone, are typically made up of two types of metals, all right? Now, that's a simplistic view. They're more complex batteries, like your cell phone batteries, which are quite high-tech, might have a metal and then a separate, different type of compound. But for the simplest way of saying it, they're made up of two metals. Most of your batteries contain lithium. You've probably heard of lithium-ion batteries, right? There was a problem with Samsung's lithium-ion batteries in their Note 7s, and that's why they're that you need to keep working, Adam. You need to keep focusing there. And their batteries were blowing up. They were exploding. So these were lithium-ion batteries. So lithium is one of the metals in it. The very first batteries to be made were made by a guy by the name of Alessandro Volta, and hence the word volt that we use to describe how strong a battery is comes from that guy's name. And essentially, he created a battery by putting two different metals, let's say zinc, and it could be, it doesn't have to be, we could do it with zinc and magnesium, might as well, magnesium. We could use the same stuff that we use for our single displacement reaction, and you needed to put it in a conducting solution. And he used an acid to begin with. All right, that was the solution that he used. And when you connected then this to a particular thing, they didn't have light bulbs back then, but it created a little spark in there. There's me trying to draw a little spark in there. So batteries need to have a conducting solution, okay? An acid or a base works great. Doesn't have to be an acid or a base, but they tend to like to use the acids or bases. And then they have to have two different metals that are in that acid and base. And then you can connect that just like you could put a light bulb in here. You could put a light bulb instead. I guess in theory you could connect it to a cell phone charger, and that would then charge it. Okay. The lemon, when you'd have to put metals into the lemon. All right. And the problem with citrus fruits to do this type of thing is that, you know how in citrus fruits there's those little segments? You know how when you take a piece of orange, you take a piece and it's got skin on that little piece? That skin is not conductive. So it would prevent the electricity from flowing. So you'd have to get your metal within the same segment in the lemon. Do you know what I'm talking about? Do you understand what I'm saying? Okay. So if you did that, and then you squished it a little bit to break all those, you know how there's little tiny pieces within the segments? Those little tiny pieces have skin. You'd need to squish that all up so all that liquid could flow freely. Then you'd have a little battery. All right? But it would not be very strong. So you'd need to do it with about 10 of them and put them in a row. Then you'd have maybe enough energy to charge your cell phone. Okay? Did you see that online somewhere? Someone charged your cell phone with some lemons? Oh. Oh. Watermelon, I don't believe, is acidic enough. There's lots of water, but I don't know if the water in the watermelon is conductive enough. Okay? But yeah, you could do that. You could. It's not necessarily the acid that makes it special. It's the fact that the acid is conductive, which is what you were thinking about, but you also need those two metals. You've got to have the metals. They're the most important part. Okay, that's a good question. Let's talk about the pH scale. All right. So the pH scale, and I'm going to just bring the whole thing up here. Oops, too far? Nope. Yep, too far. The pH scale is a numerical scale that tells you how strong an acid or a base is. You might think that it's a subjective scale. Gee, how strong do you think that is? Ooh, that's really sour. That's got to be a 1. You know, like someone just decided. But it is actually a mathematical scale, all right? In grade 11, I will teach you on how we can calculate the pH of a particular solution, all right? But for now, for you guys, just think of it as a scale that kind of measures strength. But we could calculate what the pH of this 0.1 molar solution of acid is. Now, molarity has no meaning to you. I have to teach you in grade 11 what a mole is. You guys are thinking of a little furry animal probably at this point, but in chemistry, it's actually a measurement of chemicals. And then I have to teach you how we calculate concentrations, strengths of solutions. And once we've done that, I can then tell you how we can go from a concentration of acid to a pH. And that's the steps involved. So the pH numbers indicate how strong that acid is. All right? Strong acids have a very low pH. You might think that's crazy. That makes no sense. But the equation that we use has a negative in it. And that negative flips everything around. You might think strong acids should be way up there, but because there's a negative in the equation, the strong acids are way down there. That's what the negative does to the mathematics. So low pH is a strong acid. This particular acid, if I made the solution properly and I did my calculations correctly, this would have a pH of 1. All right? This 0.1 molar. All right? This one here, this HCl, would have a pH of close to 0. It goes down to, it would be very close to 0. It would be like 0.1. All right? So this is much stronger than this one. You might think, there's not a big difference between a pH of 1 and a pH of 0, but this has a concentration of 0.1, and this has a concentration of 1. 0.1 HCl would have a pH of 1, and 1, and I'll put a big capital M in there, 1 molar HCl has a pH of 0. And this perfectly illustrates the effect. It's a power of 10 effect. This is 10 times stronger than this. 0.1 is 1/10 of 1. So when we change the strength of an acid by 10 times, the pH number only changes by 1. The pH number is actually a measurement of the exponent on a power of 10. If I were to write this as an exponent, this would be 10 to the 0, right? Because 10 to the 0 is 1, right? Anything to the exponent 0 is 1 from mathematics. This would be 10 to the negative 1, and you'll notice that that power of 10 changes by 1. That's what pH measures. It measures 10 times the strength. So when you go from a pH of 0 to pH of 1, it's 10 times weaker. The acid is 10 times weaker. You go from a pH of 1 to a pH of 2, it's 10 times weaker again. All right? Let's write some of this information down on a pH scale. Now, I'm not a fan of, here, let me show you how this should be done. I'm not a fan of having things come up on a screen, but I do want to make a video of it. So for those of you who want to write a pH scale, you can do it like this. If you're really anxious about the way your notes look, you can grab your ruler at this point. You're going for the ruler, Josie? Josie's going for the ruler. All right. So those of you who are anxious about the way your notes look, you're going for the ruler, and you're going to want 14 centimeters, because we need from 0 to 14. So put your ruler down, make a line from 0 to 14. For those of us who aren't that anxious, Bailey, that's you and me, right? We're not that worried about that. Here's the way it's going to look. I wouldn't even use this line. You'd draw a line like this. Draw a line. Like that. Bailey, go ahead and draw that line. So those of us who are anxious about the way our notes look, 0 to 14. Those of us who aren't, draw a line. Nice. It's okay. We don't need to draw a line every time. So here's what you were going to do. Those of you who are anxious, you're going to put a little mark on each of the centimeters. 1, 2, 3, 4, 5, 6, 7, 8. So they're all perfectly 1 centimeter apart. For those of us who aren't anxious, we're going to do this. We're going to go there, and we're going to go there, and we're going to go 0, and we're going to go 14. And then we're going to kind of look at our line, and we're going to kind of aim for the middle, and we're going to put a 7. And now ruler people are fighting with their rulers, trying to find 7. Those of us who aren't, we're still just drawing away. In the middle here, we're going to put neutral, neither an acid or a base. Down here, we're going to put strong acid. And up here, we're going to put strong base. Yep, excellent, right on that folder, perfect. And now I'm going to fill in some of the rest of the numbers. Again, for those with your ruler, you've got your nice little centimeters. For those of us without, we're just going to kind of look at this and go 1, 2, 3, 4, 5, 6. And we're not going to stress over the fact that some of them might look a little bigger than others. You guys can just put that right on the folder there. And then I'm going to keep on going 7, 8, 9, 10, 11, 12, 13, and I'm not concerned whether some are a little bigger than the others, because it doesn't concern me. Good morning. Not here. You can go. And I'm going to put here a 6 and an 8. And I'm going to put here weak and weak. Again, weak acid and weak base. All right? some various pHs that are not important. I'm not going to make you list these things off, but it turns out that blood has a pH of 7. All right, our system is designed to keep the pH of blood quite neutral. It's funny because Facebook, I see all the time things coming across where it's like, oh, if your blood is too acidic, it can cause cancer. Like what? Or if it's too basic, it'll cause cancer. That's the primary. It's some of these sites that tout that they know how to solve all the problems of medicine, because your blood is either too much this, too much that. It tells you what to eat so that your pH is proper. Blah 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 blah. Anyway, so blood typically around 7. If you're having things like orange juice, you're down into the 3 and into the 2. Regular rain, when it just rains, regular rain, it's about 5.5, 6, slightly acidic. That's because there's carbon dioxide in the air, and as it rains, the rain gathers up some of that carbon dioxide, and just like making pop, it creates a little bit of carbonic acid, and so rain is slightly acidic, regular rain. If you have a situation where you might have a coal-fired power plant that is burning a lot of carbon dioxide because it's burning coal, it might be burning some sulfur to produce some sulfur oxides, then you can also get what's called acid rain, which contains some sulfuric acid, and that can be in the 3 and high 2s, all right? And that can damage plants, and it can damage things that are made of marble, made out of carbonates, because it'll dissolve them, it'll cause them to turn into carbon dioxide. Okay. Yeah, I'm not worried about that. That's good. 7. Hey, look at how close to the middle I got, eh? Not bad. All right. So you can write that little bit down. A pH of 2 is 10 times more acidic than a solution with a pH of 3. That's what that says. And 100 times more acidic than a pH of 4. Yes? On the first slide, yeah, we've written that down. Logarithmic means it's based on the number 10. So everything's about 10s. So a pH of 2 is 10 times more acidic than a pH of 3, and 100 times more acidic than a pH of 4. And that's because it goes by 10s. So here's just a couple of practice problems to get a sense of how the pH changes. How much stronger is a pH of 11 than a pH of 10? Actually, 11 then 9, 11 then 8. A pH of 2 is more acidic. These questions are kind of worded goofy. A pH of 2 is 10 times more acidic than a pH of 3 and 100 times more acidic than a pH of 4. These are all true statements, but I don't like the fact that they've got 11 first and then 10 second. We'll talk about this here in a moment. Let's take a look at this first statement though. Here I've got a pH of 2, 3, and 4. Let's look at this first situation. From 3 to 2, that's 10 times stronger. Because every time you change a number, it becomes a stronger acid by 10 times. From 4 to 2, well, it's going to be 10 times 10. 10 for that one and 10 for that. So that's going to be 100 times stronger. Does that make sense? Every one you change is 100 times stronger. Now, here we're looking at a pH of 11. A pH of 11. And I don't like the way this is worded, because this is 8, 9, 10, 11, and we're going to 10. Now, the issue with the way this question is worded has to do with what they mean by stronger. Because I need to now head that way to make a stronger base. All right? So if I go this way, from 10 to 11, that's a 10 times stronger base. Does that make sense? We're now heading to base. So if I go from how much stronger is an 11 than a 10, I guess how much stronger of a base is a better way to put it. How much stronger? This is a base. I want to add that in there. All right? I want to add in that we're talking now about how much stronger the base is. Because as you move away from 7, it gets stronger as an acid and stronger as a base. So how much stronger is it? How much stronger is it? Garrett? 10 times. I wrote it down there. But what I wanted to stress to you was, now that even though we're moving to a higher number here, we're still getting stronger, but we're stronger as a base. Here, we're going to lower numbers. We're getting stronger, but we're stronger as an acid. So the word stronger is different for acids and bases. We're moving away from a pH of 7. 11 than 9. So now, how much stronger is the 11 than 9? So I've got my 9, there to there, then there to there. How much stronger is that base in a pH of 11 than it is a pH of 9? How much stronger? How much stronger? Yep. No, it's not 20. Nope. So you're thinking it's 2 10s, right? But it's 10 times 10 stronger. So what's that? 100 times. So this one is 100 times a stronger base. This one was 10 times. So you don't add them. It's a multiplication. All right? How much stronger, again, we're talking about base here, is an 11 than an 8? So I'm at 8. I want to go to 11. How many times stronger is that 11 as a base than the 8? How many times stronger? Bailey, what do you think? 1,000. 10 times 10 times 10. 1,000 times. All right? 1,000. Okay? Yeah, just pile it up all right there. That's okay. All right? Okay with that? So the pH scale measures strengths of acids and bases. The acids are down here at 0. The bases are up there at 14. And every step you make away from a 7, the stronger the acid or the base is, and it's stronger by 10 times. And it's a multiplication effect. Okay? So things get really strong really fast. Okay? What if you want to make it weaker? You're just heading back the other way. No, you would say that it's maybe 1/10 the strength. So it's not negative, it would be 1/10, or divide by 10. Okay? So if you wanted to go back the other way, let's say we went from a 9 to an 8, that would be 1/10 the strength, or it would be a divided by 10. Okay? All right. So that is, what do we got here? Indicators, hold on one second. How do we measure pH? Universal indicator, pH meters. And yeah, you can write that down. You can write that down. And I'm going to show you a little something right here before we move on to kind of the next one. How many more quizzes? We got one more quiz? One more quiz? You can just put it on that pile when you're done. So how do we measure pH? Well, we can measure pH with pH paper. We saw that yesterday. The pH paper were those little strips that we dipped into the acid or the base, and it ultimately, we checked it on a little code, not a code, but a little thing there, and we could tell where that value was. This? What? This? That's an acid. And this is an acid too. This is a base. And that's vinegar, so that's an acid. I've got some various acids and some bases. Some indicators change multiple colors depending on the strength of the acid or base. This is called universal indicator. And I said to you yesterday, if we were to put that onto a piece of paper and let it dry, we would have some pH paper. You can see there the last bullet says pH meters. We have some computerized equipment that we can connect this to. You may have used some of our computerized equipment when we did our lab at the beginning on gases when we were squeezing the syringe. We could connect this to that computerized piece of equipment. Down at the bottom of this thing is the meter, and we have to keep it soaking in a solution so it doesn't go dry. It's a very specialized piece of equipment. And so in this, Mr. Edgar. You see that? That's disgusting, eh? That's biology. Biology is making that disgusting. Mr. Edgar uses this to measure various pHs of enzyme mixtures that are digesting various things, and then he doesn't clean it very well, and it ends up pretty goopy. There's a little ball down there in the bottom there, and it's actually a little glass ball which has a little solution on the inside. And when you put that in a particular solution, it creates a little electrical signal, which then can be sent to the computer and then can be measured as a strength. So these work very well, unless you get them really dirty and then you don't clean them up properly. then they're going to work less well. Universal indicator, and I'll show you that a little bit right here. Let's get some water in here. So what I have here is called a magnetic stir. I can put a little magnet in there. If I turn this on, you can see that the magnet spins. It's kind of fun. So in here is a little motor that has a little magnet on it, and when the motor turns the magnet, this little magnet spins in line with it. If I put that in my water here, and I turn this on, I can get that to stir for me, so I don't have to stir. It's kind of fun. If I take some universal indicator, this is a mixture of indicators. Put some in there. We'll get a particular color based on what the pH is. You can see there it's kind of a blue-green. This was red, and now it's a blue-green. And I could get a little legend or a little key that would tell me exactly what that pH is. That's close to 7. It's likely a little lower. It's likely 6. If I were to add some acid to that, I can change the pH, and I can get it to change its color based on what that pH is. And again, if I had a little legend, I could tell you what that pH is, and I put a squirt of 1 molar hydrochloric acid, so I've shifted it down to probably about a pH of 2. If I now add some base to that, I can make that pH come back to neutral again, and I can get it to become green again. It's going to go through various colors depending on what the pH is. There you can see some purple in there. And it turned back to red, which means I haven't added enough. It's still too acidic. So we can measure pH just by looking at the colors. You're mesmerized, aren't you? I could probably hypnotize you at this point. There you can see we've gone to more of a blue than a green. We're pretty close to green. So we're close to being neutral. Oh no, we're going to lose the battle and go back to the other color. So I thought I was into the base side of things, but actually we're close to neutral. You can see there it's green. Let's swing it to a base color, and the base color for this is very purple. And there you can see we've switched it to base. So depending on what the colors are, we can determine what the pH is, and we could do this all day long. Now I'm putting the acid back into it, and I will try to turn it into the green, and we'll see whether it turns into the green or not. All right? And there it's going to yellow again, so I've added too much. All right? So now we're back to the acidic side of things. So we can switch it back and forth. What's happening when I add the acid to the base? What do we call that reaction that causes it to then go back to a base or become an acid or sit in the middle? Does anybody know what that reaction's called when we mix an acid and a base? Any ideas? All right. Our next note is on that. That's convenient. So that's the end of that one. And right now I want to talk about reactions of acids and bases and what a neutralization reaction is. We'll turn that off, and we'll get ready for a different indicator here in a moment. Well, I was hoping somebody might have known the answer to this, but I thought you lost your phone. Oh, and you're then going to continue to not pay attention to this and send messages over there? That's not a good path. I was hoping that somebody would have come up with the answer to what happens when we mix an acid and a base, but that's okay. The answer to that is we call it a neutralization. So acids and bases cancel each other out in a reaction called neutralization. All right. And I will complete that reaction in a moment. So reactions between acids and bases are called neutralization reactions. They are a type of double displacement reaction. This is a good opportunity here to remind ourselves of what a double displacement reaction is. It's going to be needed for our test on Friday. And unfortunately, many of you are following along on the device and therefore have already seen what the answer to this is. But to those of you who have not, maybe this is a good opportunity to remind ourselves of what a double displacement reaction is. Here we've got hydrogen at the front, and that hydrogen is going to behave as the metal, and it's going to come in and it's going to displace that sodium. And that sodium will then go in the place of the H. And so then again, those of you who are not necessarily looking at your screens and looking up here, we can see that the sodium is going to go Na with the bromine, Br. And the hydrogen is going to go with the OH. And what do we get when a hydrogen gets together with an OH? What do we get? Yep, H2O. We get water. And this is true for all neutralizations. We will always get water and this is a salt. So in all neutralization reactions, we have an acid plus a base to produce some kind of a salt and water. This is in general. In general. It's in general for all acid-base neutralizations. Now you might say, sodium bromide, that's not salt. I know salt is sodium chloride. Now, salt that we put on our food is actually a term that we use for all ionic solids. We just happen to ingest sodium chloride, and we call that salt. But chemists call any ionic compound a salt. So even sodium bromide is a salt, a type of salt. So for all neutralization reactions, you will always have an acid reacting with a base to produce water and then some kind of a salt, all right, is the other compound. That means something that was acidic can be canceled out by something that was basic to produce things that are neutral, okay? So they neutralize each other. Yep, don't mind that. We've got water and salt. We've got that taken care of. You can write down that thing right there. Neutralization reactions result in a solution of a water and a salt that has a pH of 7. Thank you. For this demonstration, this time I've got some bromethymol blue. And I got to put a lot in there because I've got a lot of water. Probably got way too much water in there. Let's get it stirring. Now, bromethymol blue is, well, what are my options for colors? What if it's a base? Base is, what's that? Blue. Base is blue. They both start with B. Acid is yellow. Acid is yellow. So neutral is a mixture of the blue and yellow. And that is, it's kind of a green. So in this case, you can see we're kind of at a green. It's a little more blue than green. It's a bluey green, but it's a little greenish. It's not super blue. Actually, it might be a little blue. That means that this is a little bit basic. So if I add a little bit of the acid, which acid do I want to work with here? No. If I add a little bit of the acid, I can get it to become yellow. Therefore, that's acidic. And now if I carefully add, actually I'll add a whole bunch of base. I've neutralized some of that acid. That's why the yellow is disappearing. And I've turned it into blue. So now I've got basic. What if I want to get neutral? What do I have to add? What do I have to add? Oh, that's still what? Acidic. So what happened? I added some base. A chemical reaction took place. Some neutralization happened, but I still have too much acid. If I want to get to neutral, what do I have to add? More base, because I've got to cancel out that acid that's in there. We'll add some base. Oh, darn. I added too much. color is now blue. What is this solution? Basic. If I want to get to neutral, what do I have to add? Acid. How should I add it? Carefully. I should add it carefully. So this is a neutralization that I'm doing. I'm not measuring anything. Tomorrow you're going to measure. You're going to measure how much it takes to neutralize a base. But this time I'm just kind of adding it. I want to add it carefully until I see what color? Green. By the way, I'm no good at this neutralization stuff. See? I wasn't very careful. To truly neutralize it is very difficult. We use all kinds of specialized equipment to make that happen. See what happens is it turns a little bit blue and then the reaction happens and then the acid is still more concentrated. Oh. Come on, green. Oh, when it came to experimental chemistry in university, I was not very good at it because it typically needs some patience. And I am not a patient person. It might be surprising to you, but I'm not very patient. It's not me, it's students and hockey players I have to work with that make me impatient. It's not me, it's not my fault. Is that still yellow? It's getting greenish. Am I there? No? Oh, don't go blue. Greenish? Getting close. By the way, bromethymol blue is a hard indicator to work with. And that's because green is a hard thing to determine what's in the middle. Phenolphthalein is great because it goes from being colorless to pink and then to colorless. So you don't have this in between. You have it's either colorless or it's pink. Because we're going to use bromethymol blue tomorrow. Why aren't we? All right. Well, we're close. I do have to keep going. I'm advancing here. Click. Let's do a couple of practice reactions here. All right, and then you can write down that. Oh, that's pretty green. I think we're pretty close. That's a win. That's a win. That right there, that is neutralized. Okay, let's do a couple of examples here. By the way, actually, that first reaction right there is what I did here. I put HCl with sodium hydroxide. So, what are the products in here? Not including the green, which is the bromethymol blue. What are the products that are in that flask right now? So I've got an HCl, and I've got an NaOH, and it's going to do a double displacement. I guess my question is, what is the salt? What compound is the salt? So what are the products here? Yeah, what do you got, Garrett? NaCl, the Na goes with the Cl, and what's the other product? H2O. If I were to take this, and I could remove the bromethymol blue, and I were to boil this water, and have the water all evaporate away, I would be left with a white powder, which would be salt. All right? It would be sodium chloride. It would taste like salt. You could put it on your fries if you wanted to. It might have some bromethymol blue in it. That might not be so good. But it would be salt. Let's try the last one. Sulfuric acid, H2SO4, reacts with potassium hydroxide KOH. Again, double displacement is going to happen. What are my products going to be? What's the products going to be? Well, what's one of them always for a neutralization reaction? Always. H2O. It doesn't matter whether you put it first or second. It makes no difference. What's the other product? Which one? I want to know the chemicals that are in that salt. What do we got? What's it going to be? Thomas, what do you got? K, SO4. Now, if we had our periodic tables, we would check and see that the SO4 is a -2, so we actually would need a 2 right there. Okay, because it's got a 2 and a 1. We'd have to cross that over. This is not balanced. What do we need to do to balance this? Thomas, what am I putting? Which K? So the KOH, 2 there. Okay. What else do I need? I need one more thing here. Yeah, Josie? 2 waters. Because these 2 H's get together with these 2 OH's to form 2 H2O. Okay, I had one more thing that I wanted to talk about, and I'm not going to rush that through. So we'll stop there. There's a little bit of homework that you can do there. Tomorrow, I still plan on doing the lab, but I do have one more lesson. I might change it up. We'll see whether we do the lab or not. I might switch that around. It was going to be, but because I've got one more lesson that I still have to do, it may become something else. So wait and see. We're in a wait and see mode. Okay, so I'm going to stop that.